Sorry about that, I had a technical issue. Let's see. So we are trying to find the integral of 1 over x times the natural log of x. And we broke it up into pieces and decided that we should try letting u be the natural log of x. And then du is going to be 1 over x, the derivative of that, dx. And let's see what our integral becomes. So if we make that substitution, our integral will change to 1 over u, and then it's the 1 over the natural log of x part. And if I group the 1 over x dx and dx together, everything else is going to just become du. And that's a simple integral. That's an integral we can do pretty easily. So this is the integral of u to the negative 1. And that was the special case. We can't use the product rule, because if we did, we would end up with u to the 0, and we would have to multiply. We would have to have a coefficient of 1 over 0. And that doesn't make sense. So this was the exceptional case where the product rule doesn't apply. Instead, the antiderivative is going to be the natural log of the absolute value of u plus c. Remember, the derivative of this is 1 over u, which is the same as u to the negative 1. So this answers this integral, but we want to then convert the answer to get a function of x, and that's pretty straightforward. We just need to know what u is, and u we decided to be the natural log of x. So we just replace u with the natural log of x blindly, sort of, and that's what we get. We have the natural log of the absolute value of the natural log of x plus c. And that, in fact, is our answer. If you were to differentiate this, you would get 1 over the inside, 1 over the natural log of x, I guess, times the derivative of the inside, which is going to be 1 over x. So there you go. We've solved the problem. Finally, I wanted to do one example of an application. This is going to be problem 61 in your textbook, which is a word problem. I don't want to write all the words on the board, so I'll just read it to you. It says, in calm waters, the oil spilling from the ruptured hull of a grounded tanker forms an oil slick that is circular in shape. If the radius r of the circle is increasing at a rate of r prime equals 30 over the square root of 2t plus 4 feet per minute, and that is the rate t minutes after the rupture occurs, find an expression for the radius at any time t. So the picture is this, where there's some oil spill, and initially there's no oil in the water, so the radius of the oil slick will be 0. And then as time goes on, the radius increases. We want to find the radius at time t, but all we know is how the radius is changing. We're given how the radius is changing. Now, r prime is how r of t is going to be changing. That is, r prime is the derivative of r. So to go from r prime to r, we just have to undo the operation of differentiation, which would send r of t to r prime. So we need to go the other way. We need to go from r prime to r. So what happens is that r of t is going to be a particular antiderivative of r prime. So we end up wanting to do the following integral. We want to integrate, I'm going to rewrite this expression as 30 times the quantity 2t plus 4 to the negative 1/2 dt. We want to do that integral. And it looks complicated. So what we're going to do is use substitution. And the only composition of functions that I see is the 2t plus 4 and the other function which raises that to the negative 1/2 power. So we're going to make a guess. We're going to let u be the inner function, 2t plus 4. And then du is going to be the derivative of that, which is 2 dt. So now what happens is the integral will become, keep the 30, now the 2t plus 4 will just be u, the exponent will be the same, and we're going to replace dt with 1/2 du. So basically we solve this equation for dt, and dt is going to be 1/2 du. So we replace dt with 1/2 du. We make sure that we only have u's here. So this is only a problem, only an integral that has u's in it. And then we can do the problem. So this is now going to be the integral of 15 u to the negative 1/2 du. And we just write down, we said u is 2t plus 4. So now we want to do that integral. And that integral will become, if we pull the 15 out, and now the antiderivative of u to the negative 1/2 will be u to the 1/2, and because we increase the exponent by 1, and then we need to divide by the new exponent, and dividing by 1 over 1/2 is the same as 2. And then we get a constant of integration, so we end up getting 30 u to the 1/2 plus the constant of integration. And c here is going to be 15 c1, but it's just some constant, any constant. We don't really care yet. And we can check that if we differentiate this with respect to u, we should get 15 u to the negative 1/2. And in fact we do, the 1/2 comes down, we get 15 u to the negative 1/2 because we have to reduce the exponent by 1. Okay, so we've done that portion correctly, and now finally what we have to do to find the integral of this expression is to get everything back in terms of t. So we replace u with 2t plus 4 to get 30 times 2t plus 4 to the 1/2 plus c, and that is going to be r of t. The only problem is that we don't know what c is quite yet. This is really a family of functions And there's a particular value of c which will give us the single function r that we want. But we need to find what c is in order to find that particular antiderivative. So the last step is to observe that at time t equals 0, there was no oil in the water, so the radius of the oil slick will be 0. So r of 0 will be 0 on one hand, and on the other hand, we have this expression for r, and we can plug in 0, and we get 30 times 4 to the 1/2, so the square root of 4 is 2. So we get 30 times 2 plus c has to be 0, which means that c is going to be negative 60. And therefore, the particular antiderivative we want, which will describe the radius at time t, is going to be 30 times 2t plus 4 to the 1/2 minus 60. And that's the answer to this problem. So, we're out of time, so I will see you on Tuesday.